Page 72, section 2.2, limit of a function. All right, over on page 73, they give us the definition of a limit. On page 73, red box definition, it says the limit of f of x as x approaches a equals L, can be written as you see it there in red as we just did. If we can make the values of f of x arbitrarily close to L, as close as L as we would like, by taking x to be sufficiently close to a but not equal to a. I'm not sure that I have any more understanding of what a limit is after reading that than I did when I started. So let's back up. A limit is basically what is your y value approaching as you approach your x value from the left and from the right. What is your y value approaching as you approach your x value from the left and from the right? So let's look at this example that we have here. The limit as x approaches 2 of x squared minus x plus 2. Limit of x squared minus x plus 2 as x is approaching 2. All right, so what we're saying there is as I approach an x value of 2, and I'm going to approach it from the left-hand side and from the right-hand side, as I approach that x value of 2, what is my y value doing? And we want to look at that algebraically and graphically and see what we can come up with. All right, so let's start with looking at this algebraically by using a numerical table of values. All right, if I wanted to approach 2 from the left-hand side, I would be using values like 1, 1.5, 1.9, 1.99, that type of thing. And so I'm going to draw my table so that it mimics that number line, where I could go through and put in 1, 1.5, 1.9, 1.99, 1.999. I'm just going to have it get closer and closer and closer to that value of 2. If I did the same thing from the right-hand side, if I'm approaching 2 from the right-hand side, that would be like 3, 2.5, 2.1, 2.01, 2.001. And so that's what you see over here. We could do 3, 2.5, 2.1, 2.01, 2.001. And so again, as I draw that table, notice that the way I draw the table, the x values are approaching from the left and from the right. They're approaching that x value of 2. I want to figure out then what the y values are doing as I'm approaching an x value of 2 from the left and from the right. So I'm going to go through and I'm going to plug those values into my calculator. So grab your graphing calculator if you would. Put that equation in y equals. So your equation was y equals x squared minus x plus 2. So throw that in y equals x squared minus x plus 2. X squared minus x plus 2. All right, and then I'm going to go to second trace, which is my calculate menu. And I'm going to choose my value button. And I'm going to type in any one of those x values from the table. I chose 1.999. And it's given me 3.997001. Everybody getting that to work? Okay, so once you know how to do one of those values, instead of making you sit here and plug in 8 different values in your calculator for every single example that we do today, as long as I know that you can generate those values, then go ahead and fill in the rest of the values from that table that you would have gotten by using that value button on your calculator. You also can use the table button on your calculator, but the only problem is on my table button, it's either going to count by like whole numbers, which if it counted by whole numbers, I could get this value and this value. But then I would have to change my table set so that it was counting by tenths in order to get the 1.9 and the 2.1. And then I would have to change my table set to count by hundredths to be able to get the 1.99 and the 2.01. And then I'd have to change it to thousandths. So it's whatever is easiest for you, but I think we might find it faster just to use that value button to create that table. Now, there's not a set number of decimal places that you have to use when you're creating a table of values. The key is that I need to see a change. We're looking for what is the y value approaching as x is approaching 2. So I need to see a change in my y value. Like right here we had 3.7 and then we had 3.97 and then we had 3.997. I can see a change there. I would not want to round each one of those values to 4 and go through and say 4, 4, 4. I need to see a change from entry to entry in your table. Okay, same story over here. We've got 4.3, 4.03, 4.003. I would need to see that change in your table. So any questions about how to build your table? Okay, then let's look at how to interpret that information that we get from the table. We can look at this and say, okay, if the limit of this function as x approaches 2 is what my y value is doing, as I approach 2 from the left and 2 from the right, then let's look at these y values. I've got 2, 3.7, 3.97, 3.997. I start to notice a pattern, right? Where I could say, if I did 1.9999, what would your guess be as to what we would get for the y value? Yeah, 3.9997. It's as if as I enter another 9 up here, it enters another 9 down here. So if we expanded that, we would end up with 3.999999997, depending on how many decimal places we kept plugging in, right? So looking at those values, what would you guess that limit from the left to be? 4, right? It is an absolute guess. It's an educated guess, but it's just an absolute guess. All right? Look at it as I come from the right-hand side. From the right-hand side, I've got 4.3, 4.03, 4.003. What do you think the next entry might end up being? 4.0003, right, or 4.000003 if we kept going. So from the right-hand side, what does it look like those y values are getting closer and closer to? 4. Now, the idea of a limit is it is a target. It's a goal. It's a bullseye. I want the piece of my graph from the right-hand side and the piece of my graph from the left-hand side. I want both pieces of that graph to be converging on one y value. And that one y value will be my limit. So for that reason, it's very important that the y value that I think I'm approaching from the left has to be the same as the y value that I think I'm approaching from the right. Or both pieces of my graph will not be converging on one point. So in a little bit, we're going to call that the limit from the left and the limit from the right. So we might as well start using that terminology now. The limit from the left must be equal to the limit from the right in order for that limit of 4 to exist. So when I looked at it numerically, it did look like all of the y values were converging on 4 when all of my x values were converging on 2. So I could say that limit is 4. And again, if I looked at the graph, I could say from the right-hand side and from the left-hand side, both pieces of my graph appeared to be converging on that one y value, and that one y value is 4. Now, we stressed the fact that this was just a guess. Over on page 77, there's a little Ghostbuster symbol on the top of the page. Remember, that's those things of watch out for these types of common mistakes. It says, examples 4 and 5 that we're going to look at in a few minutes illustrate some of the pitfalls in guessing the value of a limit. It is easy to guess the wrong value if we use inappropriate values of x. But it's difficult to know when to stop calculating values of x, like we'll see in the discussion in example 2. Sometimes your calculator can even give you the wrong answer altogether. Fantastic. However, in the next 2 sections, we will develop foolproof methods for calculating limits. We are trying to get an intuitive understanding of what a limit is and why those methods that we're going to learn in the next 2 sections work the way that they do. So yes, we are just flat out guessing what the limit is here, and sometimes we're going to guess wrong because of the limitations that they just stated, but keep in the back of your mind that we will get foolproof methods for evaluating limits in the next couple of sections, so don't let it frustrate you. that we're just guessing right now, okay? Now, some of you are looking at this example and going, Ms. Wetmore, if I know my x value and I want to find my y value, how come I don't just plug into the function? I mean, if I take 2 and I put it in place of x, 2 squared is 4, minus 2 is 2, plus 2 is 4, I get my limit just as easy as that. Well, that type of function where I can do direct substitution we mean to put 2 in the place of x in that function. If I have a limit where I can do direct substitution and come out with the actual correct limit answer, that type of function is called well-behaved. How many of those you think they're going to give us on the homework?
0.
Maybe 1 if we're lucky, right? So yeah, I could have done that on this problem, but that's not going to be the norm. So let's look at a couple of scenarios. This first example that we have here would be an example of a well-behaved limit. That is that if I look at the limit as x approaches a from the right and from the left, all of those values are converging on one y value, and it just so happens to be my limit. It's defined at that point. There's no craziness going on. It's just well-behaved. It's normal. But let's look at a couple of other scenarios. That definition of limit on page 73, probably the most important part of that is the last 5 words in that definition. On page 73, when it talks about taking the limit, it says we need to look at values close to a, but not equal to a. When I am looking at a limit, I do not care what is going on at the point. I only care about what is going on as I approach that point from the left and from the right. What is going on at the point itself is completely irrelevant. It does not even have to be defined at that point. Here's what that would look like. If I had a function that was undefined at a, there will literally be a hole in my graph at a, right? But I can still calculate the limit, because as I'm looking at what are the y values doing as I approach from the right and from the left, all of them are converging on that one point. That is my limit, even though the function doesn't even exist at that point. They could even go back, and if the function didn't exist at that point, they could redefine the function at a totally different point. It still would not affect my limit. If you'll notice, my limit is still going to be up here because the values from the left and the values from the right are all converging on one y value, and that is my limit. I don't care what is going on at the point. It can be undefined or it can be redefined as a totally different value, and it will not affect my limit at all. All right, look at example number 1, bottom of page 73. It says guess the value of the limit. That's exactly what we're doing. We're just flat out guessing. Guess the value of the limit of x minus 1 over x squared minus 1 as x approaches 1. Ooh, let's try that direct substitution thing, right? Because that was really nice when it worked. What happens if I use direct substitution here? I get 0 in the denominator. Now, last year you might remember from the discussion that we did on limits that there are some times that a limit will not exist. Just because your limit is not well behaved does not mean your limit does not exist. Just because you can't do direct substitution and go straight to your answer, that doesn't mean your limit doesn't exist. It just means it's not well behaved, and you're going to have to approach this a different way. You're going to need to use a table. You're going to need to use a graph. Okay? So let's start with a table. If I'm approaching 1 from the left-hand side, I would use values like 0, 0.5, 0.9, 0.99, 0.999. If I'm approaching from the right, I might use like 2, 1.5, 1.1, 1.01, 1.001. So again, I would use my calculator to go through and make that table of values. When I am drawing my table, I'm going to be the one choosing what x values to use here. When I'm drawing that table, make sure that that table mimics your number line, that those values get closer and closer to x the way that you set up that table, that my x values approach 1 from the left and from the right. Also make sure that the values that you enter change. So like we've got 0.52, 0.502, 0.5002. Over here we've got 0.47, 0.497, 0.4997. There needs to be a change. Okay, so let's look at it from the left. If I've got 0.52, 0.502, 0.5002, we could kind of generalize that. It's going to keep going 0.50002, right? So what would that limit appear to be approaching from the left-hand side? 0.5. From the right-hand side, I've got 0.47, 0.497, 0.4997. So if we kept going on with that, we would probably get things like 0.499997. What does that look to be approaching? 0.5. So since my limit from the left equaled my limit from the right, it does appear that all of my y values are converging on one particular value, and that is 1/2. The function was not even defined at 1, but I was still able to find the limit of 1. What I'm looking at is a scenario exactly like this one, where the function does not exist at 1, but I'm still able to find the limit. And if you'll notice there in your textbook, on page 74, they do graph that function. And sure enough, if you look at that graph from the left and from the right, both pieces of your graph are converging on the same y value of 1/2. What if we redefine that function? It's 1 that's causing me grief, right? When x is equal to 1 and it gets 0 in the denominator, it's undefined. So what if they rewrote that function as a piecewise defined, and they said, okay, use that same equation you just had for every other value except for 1. But because 1 is the problem, when x is equal to 1, let's redefine that as 2. How does that affect my limit? It doesn't. Exactly. That is completely irrelevant to my limit. It does not affect the limit at all. I don't care what's going on at my point. I only care what's going on as I approach it from the left and from the right. So that would be this scenario that you see right here, where the function didn't exist at my a value, so they went through and they redefined the limit at some other point. It doesn't matter. It is completely irrelevant to my limit what is going on at that point. I only care about what's going on as I approach it from the left and from the right. So at this point, some of you are already starting to think of some shortcuts. For instance, you're looking at this going, there's really no need to build that whole table, because I could just use this inside piece right here. If I saw this was 0.500 and this was 0.499, I would know my limit was 1/2, and I could save myself a lot of time and energy. Well, there are some limitations to this process with the calculator, and that is one of them. Let me show you an example using example number 2 of why you wouldn't want to do that, why you wouldn't want to take that out of context and just look at the innermost values. If I were to do that on example number 2, where I basically say, hey, I'm just going to examine these innermost pieces and let them determine my limit. If I went through and I built the whole table, I've got 0.1666, so 3 6s here, 2, 3 6s here, 7, 5 6s here, 7. So that would lead me to think that this is 0.16 repeating from the left. But my calculator runs out of a number of decimal places that it can maintain, and so it starts rounding. And so when it gets to this guy, it tells me 0.2. Same thing happens on the other side. So if I build the whole table, I'll recognize that and go, okay, this was approaching 0.16 repeating, but it just ran out of space here and it rounded off. If I only looked at those innermost values and I didn't look at the whole table, I would be tempted to say that my limit was 0.2. And if I went even further and I used an even smaller number, like some people like to just use one really, really, really small number and use that as an indicator of their limit, if I did that, I would say this limit is 0, and that's definitely not the case. So that's the significance in building the whole table as opposed to just looking at 1 or 2 very small values. And that's the caution that they were giving me on the top of page 77 when they say it's easy to guess wrong if you don't use appropriate values for x, but how do you know how far is too far to go? I mean, I'm trying to be even more precise here, and instead it ends up leading me to the wrong answer. So again, that's why this is just a guess, and we're going to get some methods for this, but that's why we want to use the whole table, and we also want to look at the graph as a backup for our table. Here's another example. For example number 4, here's another limitation that your calculator has. If I go through and I'm approaching 0, so that looks like the typical table that we've used for approaching 0. I go through and I plug those in. Every single one of those gives me a value of 0. So my guess would be, okay, that limit is 0. When I look at the graph, however, I find something totally different. That limit actually does not exist. Because when I look at the graph in zoom decimal, I'm like, I don't have a clue what's going on there. So I zoomed in a little bit to try to see what was going on. And it doesn't matter how much you zoom in this region right here, it looks the same. Because you have an infinite oscillation in the center of that graph. It just keeps going up and down nonstop. That whole graph is not converging on one particular y value. So that's why that limit does not exist. But it would be hard to find that just by making that table of values with my calculator. That could lead me astray. So again, we do want to get some actual methods to help us out with that guessing process. Now, I don't want you to think that every time you see a sine or a cosine function, it's always going to be does not exist. Yes, sine and cosine do go back and forth between 1 and -1 nonstop. However, they don't do it an infinite number of times at a point. Like here's the limit as x approaches 0 of sine x over x, and this is what that graph looks like. If you look at that graph there on page 75, if you'll notice, as you look at the limit from the right-hand side and you look at the limit from the left-hand side, both pieces of that graph are converging on one y value. What are they converging on? 1, yeah. So that limit absolutely is 1. Because the limit from the left did equal the limit from the right. Both pieces of that graph are settling on one precise specific value, and it's 1. So yes, I could find that limit. So then over on the bottom of page 77, they state something that we've actually been stating all through this lesson, that your limit can exist if and only if the limit from the left is equal to the limit from the right. I need both pieces of my graph to converge on one particular value. Here is their notation that they're going to use for limit from the left and limit from the right. They're going to put a little negative as a superscript, or like in the place of an exponent, for left, and they'll put a little positive for right. So it would look like this. This would be the limit of g of x as x approaches 2 from the left, and this would be the limit of g of x as x approaches 2 from the right. Okay? So for example number 7, they give us a graph and they ask us to evaluate some limits by looking at that graph. I don't have equations this time. All right? So I could go through and I could say, let's take the limit as x approaches 2 from the left. So here's 2 right here. If I'm approaching 2 from the left, I'm coming in this way. So I'm going to come in on that graph approaching 2 from the left. What y value does it look like I'm approaching? 3. So that would be my limit from the left. All right, now I want to take the limit as x approaches 2 from the right. So again, here's 2. If I'm approaching it from the right, then I'm using values coming in like this. So if I come in on the graph approaching 2 from the right, what y value does it look like I'm approaching? 1. So what is the limit then as x approaches 2? It does not exist. Nice. Why? Because they're not equal to each other. Exactly. The limit from the left did not equal the limit from the right, so the limit doesn't exist. Look at the graph. Yeah, like all of you have Mean Girls running through your mind right now. I know. All right, so if you look at this as I'm approaching 2 from the right and 2 from the left, are both pieces of that graph converging on one point? No, so you could look at the graph and see that limit doesn't exist there as well. All right, look at the next piece. Find the limit as x approaches 5 from the left. So here's 5 right here. As I approach from the left-hand side, what y value am I approaching? 2. Then it's the limit as x approaches 5 from the right. As you approach from the right-hand side, what y value are you approaching? 2. Then they asked me to find g of 5. Remember, that means when x is equal to 5, what is y equal to? So I can come down here and say, okay, when x is equal to 5, y is equal to 1. What bearing does that have on my limit? None. Absolutely. It is completely irrelevant. I don't care what is going on at that point. I only care about what is happening as I approach 5 from the left and from the right. So when I approach from the left, I got 2. When I approach from the right, I got 2. So what is my limit? 2. Even though g of 5 is equal to 1. Completely irrelevant. All right, so here is our homework for tonight.